Thanks for joining me, everyone. My name is Ethan Raito. I'm the Director of Marketing here at Mantle. Today, we're going to be talking about designed for the shop floor and talk about 9 different unique ways that Mantle is designed specifically for your shop floor and is easy to use in your tool room. Goes without saying, but feel free to use that Q&A section. If you have any questions throughout, just throw them in there. I can take them as we go. I can answer a bunch of questions at the end. I have a couple different parts with me here today I'll be talking about throughout. But let's go ahead and get started. And thanks a lot for joining me. So a quick agenda for today. We're going to do a brief introduction to Mantle, who we are as a company, and a quick overview of how our technology works, because a lot of how our technology works is what enables our system to be so easy to deploy on your shop floor. We'll take a look at what makes Mantle the only metal 3D printer that's designed specifically for tooling. We'll look at the 9 different ways Mantle was designed to go specifically onto your shop floor, and we'll do a questions and answers throughout, as well as, of course, at the end. So let's jump right into talking a little bit about who Mantle is. So Mantle's goal is to automate your toolmaking processes. The way that we do this is by printing precision mold components with unmatched accuracy, surface finish, and tool steel performance to allow you to really automate most of the toolmaking process and remove those time-consuming and expensive steps of the toolmaking process, like programming, rough milling, and the EDM process. What this allows our customers to do is really unlock a game-changing speed, cost, and efficiency. You're able to produce tooling in less time, less cost, and actually produce more efficient tooling. Things like conformally cooled tools and advanced vented tools to allow you to actually get more out of your tools than you could with a conventional process. But all in all, who Mantle is as a company and what we do at Mantle is that we've designed the only 3D printer that's designed specifically for printing tooling. We designed it from the ground up with specifically injection mold tooling in mind. We've expanded that a little bit into new applications such as extrusion and MIM and die casting, but today mostly injection mold tooling because we designed this printer specifically for that application. To talk about how our technology works, which is really going to help you understand a lot of the things that enable this system to be easy and efficient to deploy on your shop floor, it all really starts with our metal paste. So at Mantle, we're printing a metal paste. You never would guess that when you see, our final parts that are tool steel, very, very hard, precise parts. But these all start as a metal paste. That paste has the consistency similar to a toothpaste. It's a combination of metal powder mixed with some binder and some solvents to allow it to flow. Um, Inside of our printing system, every single layer, we are going to print a layer of this paste. We're just extruding that via a deposition process, very similar to the inexpensive FDM printers you could probably buy anywhere. But what we're printing instead of a filament is we're printing this paste material. It's viscous enough that we don't even need to heat the material. We simply are pumping it through a deposition nozzle and laying it down layer by layer. After every single layer has been printed, we're going to go through and dry that layer. That's actually removing some of the liquid that was in that paste and kind of firming it up. After it's been dried, it's kind of has the consistency of a dense foam. So in this stage, it's removed some of that liquid. We've kind of turned it from a paste into kind of a foam material, but it's still relatively soft, mostly made of here metal powder and a little bit of binder to hold it together. This is where the kind of some of the magic starts to happen. But after every single layer, we are going to machine. So we are building our printer inside of a CNC machine, which we'll talk about later on. But every single layer here is being machined perfectly flat. Since we're essentially machining a dense paste or dense foam that is only one layer at a time that we're machining, we can use some very, very small cutting tools and machine very quickly. The smallest cutting tool we're using today is going to be a 6 thou ball and mill, so 0.006 inches. So I don't know, it probably doesn't come across great on this webcam, but some really, really crisp, fine details that we can machine with those tools that gets you very, very close to a dead sharp like you would have in an EDM process, which is a pretty common theme with our technology of our customers looking to reduce or eliminate the amount of secure EDM work they have to do. So every single layer in the printer, we're printing, we're drying, and we're shaping. I should have mentioned that again, we're doing this every single layer, which allows us to have something very, very flat to print on every time, as well as remove those layer lines and touch up and add some feature detail that you couldn't have printed. After the printing step is complete, our parts are going to go directly into a sintering furnace. So here we're taking it from this kind of dense foam and turning it into a dense, hard tool steel component. Today, that means H13 or P20 tool steel, but we're ending up with a dense, hard material that can be used directly for injection molding or other tooling applications. I should note that when parts do come out of our furnace, they can be very easily have things like machining done to them. They could have wire EDM done to them, secret EDM, grinding, any of those operations you do in your normal tool shop. You can always take our tools and do that to them if you need to, for example, get an A2 finish because the D2 finish that we deliver isn't good enough. So all those operations, of course, are fully compatible with our technology. So just to show you a quick video of this actually working, you can see with inside of our printer here, actually laying down that paste material. So we're laying down that metal powder mixed with those two different liquids. We're going to dry it to remove the solvent specifically, remove some of the liquid out of there, and then we're going to go through and machine it. So every single layer, we're repeating these steps to build up our part one by one. So that's all happening inside of the printer that you're seeing here. Happening inside of the furnace is where we're doing our sintering step. I know it's an animation here, a little bit harder to get a camera into a high temperature sintering furnace, but here we're turning the part from that dense sort of foam material into a tool steel part like you're seeing that I have on my desk here today. Awesome. So it's great to have this sort of fancy printing technology, but what does it actually deliver? It delivers a Synchro EDM style finish, so a matte finish, 1 to 3 micron RA, a Charmy 26, similar to a D2 finish. So your parts are going to have sort of a matte surface finish on them. Best in class precision for metal 3D printing, plus or minus 1 thou per inch. So on a 3-inch part, you'd be looking at plus or minus 3 thou. Very, very fine features and crisp features, since we're using those very, very small cutting tools, features as small as 3 thou corner radius, which is very similar to those EDM sharps that most people are after. Stable, durable tool steels, like I mentioned, that H13 tool steel. Very, very easy system to use, no programming required, and of course, that ability to incorporate conformal cooling to reduce your cycle times. So these are kind of all the specs that we are able to do. As I mentioned earlier, it's fun to have a cool printing system, but what does it actually deliver? All these specs. What do these specs actually deliver? It delivers real-world results. Our customers are looking at reduced lead times, reduced costs. The example on the left, relatively large slide, 75% less cost, 75% less time. This component in the middle, 67% less cost. This is an insert for actually producing a dishwasher component, 71% less time. And then on the far right, this is an example for actually molding a high-volume deodorant component, 60% less cost, and those inserts have run over 1.7 million cycles each. We've produced 2 of them here for Tessie, so over 3.4 million parts produced for these inserts, just to kind of show the durability that these materials have. So now that you have a little bit of an understanding of Mantle's technology, I'm going to jump into the 9 specific ways that Mantle is designed for your shop floor. When we looked at addressing the tooling industry and designing a system specifically for tooling, we knew that meant, of course, achieving the tolerances, the surface finish, and the properties needed for these tooling applications, but also designing a system that could be easily incorporated onto a tool shop floor. We looked at a lot of the existing metal 3D printing technologies, powder bed fusion and binder jet technologies, which are great, very capable technologies, but in general, they're just not accessible for most tool makers and molders because of a lot of the facility and expenses that come with those systems. And we'll talk through how Mantle kind of designed this system to really eliminate those. The first one, which if you're familiar with metal 3D printing and other technologies, you're going to be familiar with this need for loose metal powder. Technologies like powder bed fusion or binder jet technologies require you to use these loose metal powders to actually form your part, which then requires quite a lot of extensive PPE, respirators, as well as the need for special ventilation and all sorts of other hazards that come with handling loose metal powder. You're not going to want to have that get in the air, obviously, and inhale it, or also actually carry some explosion hazards just because of how fine some of those particles can be. As we just talked about with our pace, Mantle eliminated that concern, designed the system to go on your shop floor, which is how we were able to create this paste material. You're not exposed to any loose metal powder. If you spill a little bit, all you got to do is wipe it up with a little isopropyl alcohol and you're good to go, which eliminated all the risks that are associated with these loose metal powder technologies, making it super simple and super safe to put on your shop floor. The next is this need for solvent debinding. A lot of metal or other extrusion-based, binder-based, MIM-based technologies that require extrusion require a second solvent debinding step. This is actually being used to remove the wax that's in the material that is needed for their printing process because they're melting the wax to be able to flow that metal powder and that binder. This is generally done with a vapor degreasing process where you're immersing your part in this for a day or as much as a few days to remove that wax out of the part before it can go into the furnace. With Mantle, our parts are going directly from the printer into the furnace, so we don't need any of that debinding separate solvent debinding step, eliminating the need of bringing in those debinding fluids, those systems, and understanding that process. The way that we actually enable that to happen is because every single layer we're drying. So we're removing that solvent that we're also using to flow our material. We're removing it every layer by simply drying it out. We're not printing and then removing it afterwards. Every layer we're removing that solvent. So we're essentially debinding the part in process and removing that solvent right out of the part, rather than having to do this separate immersion solvent debinding step to remove the wax that they use, which is quite different than what we're using in our process. Standard shop power and air. Our printer system is built on top of an existing robo drill CNC, a very, very common tried and tested machine. We source it actually, we heavily modify it for our printing process, but because we are sourcing and building on top of something that most tool shops already have, we are not needing any extravagant shop power or air requirements. Both of these standards are pretty consistent with what you would see across a tool shop floor and across most manufacturers that have CNC equipment, which means you're going to be able to drop this machine right next to your existing equipment and not have to do these crazy changes to your building facilities requirements, your power requirements, and air requirements to get this thing up and running. This is one benefit that actually I kind of underestimated when I first working at Mantle, but this idea that there's no programming required. When we talk to a lot of tool shops and precision manufacturers, they tend to tell us that traditional CAM software and other metal 3D printing softwares are incredibly complex. They have very, very steep learning curves. They're expensive. And that if you do have a CAM programmer, you better hold on to them tight because they're very, very valuable to your organization because they understand the inner workings of this CAM software. It's a huge value add to your organization. And they're very, very hard to come by. Someone that understands these very, very complex, expensive, and difficult to learn softwares. So we thought, how can we remove this barrier? How can we remove this hurdle? So we designed a system that doesn't require any programming. Mantle software is extremely easy to use. We're going to generate all those toolpaths for you in minutes, both the additive and the subtractive toolpaths, which is pretty incredible that in just a couple of minutes, you can load your part. It's going to automatically generate everywhere you're going to deposit material. It's also going to automatically generate everywhere that the subtractive tools are going to come back and remove material. There's no programming required, no CAM experience required, and really I could train anyone on this call how to do this in just a couple of minutes. We have whole other webinars dedicated to how our software works, and I encourage you to go and check those out because it's really, really the brains of the system and allows this thing to be super easy to use and super fast for you to get up and running and using. This idea of no lasers or special rooms, Mantle's technology is combining the most popular method of 3D printing, which is material extrusion, with a tried and tested CNC machining step. So we're not using some exotic printing method, such as a laser-based system. We're simply combining two very, very well-established and safe processes, material extrusion and CNC machining, to allow you to produce beautiful parts, but with machines that sit right next to the equipment that you already have on your floor. You don't need these special environment rooms or explosion-proof rooms that you sometimes need with these powder-based processes because you have to worry about those loose metal powders. You don't need these special ESD requirements for static and things like that. These machines are designed specifically to go and sit next to your equipment that you already have. The one piece of equipment in our system that is a little bit foreign to most tool shops and to a lot of manufacturers is our need for a sintering furnace. This is the piece of equipment that's going to allow you to take your part from that dense kind of foam-like material and sinter it into a dense, strong metal part. What's actually happening in the sintering step is the furnace is going to get just below the melting temperature of the material. It's going to remove that binder that's left in the part. Your part's going to shrink a little bit, and the metal powder is actually going to have high enough energy, allowing it to sinter and densify together, closing up all the porosity that you have within inside your part. That could be kind of a scary idea for some people to be able to have to run these high temperature furnaces, but the system is designed to be incredibly easy to use. You literally load your parts in it, and press go. There's a couple predefined recipes that are just based off of time, 24 hours, 32 hours, 36 hours, that are really just defined by part size. If a part's really big, you're going to want to hold it at temperature for longer and let it cool slower just to ensure that you're getting the best properties possible. If the part's really small, you can usually run that a little bit faster. So all that's predefined for you. Super, super easy to use furnace. Just load your parts in and press go. The furnace is what's called a vacuum furnace, which means it's pulling vacuum before sintering. The reason for this is because, as you probably know, with things like welding or other temperature processes, when things get very, very hot, they tend to oxidize very, very quickly. So in order to inert this environment, ensure we have a very, very clean sintering environment, two things are happening here. First, we're going to pull a vacuum to remove all the air out of that chamber, and then we're going to flood with an inert gas. The gas that we use in our process is going to be a nitrogen gas. This is a very, very safe and inexpensive gas that you can actually source from your existing welding supply chain usually. It's inert, it's non-hazardous, it's not explosive, unlike some of the specialty gases required for other processes like a hydrogen for some sintering processes or argon or some other materials that can be relatively challenging to work with, or I should say more challenging than the nitrogen gas. The National Fire Protection Agency rates this as 0 across the board for all these different health hazards that you're going to want to look out for. So even though there is this little bit of a foreign process of sintering involved, very easy to use and using a very, very safe and inexpensive gas to use that actual sintering process. Lastly, this idea of being cost effective. For most tool shops, molders, manufacturers, the thought of buying $1 million metal 3D printer is really just not possible. It's, maybe they're buying a machine or two machines every year or every couple of years. So to spend a couple years of capital expenditure budget on one machine is really, really challenging. So we designed our metal 3D printer and our technology to be very, very similar in cost to CNC and EDM equipment, technology that shops are already used to purchasing. On the other side, very, very low cost per printed part. For tool shops, are not looking to be printing, $5,000, $10,000 specialty parts. So we designed, and I'll show how this actually works, where we're kind of designing these technologies to produce relatively inexpensive parts. Starting with the machines, we're very, very upfront with our pricing. Our printer is going to cost $230,000. The furnace is going to cost $120,000. The reason we separate those is just because one furnace can support multiple printers. So we have customers that have multiple machines, but only one furnace. But again, we're very, very upfront with our pricing because we feel it's very, very competitive with equipment you're already buying, and very, very easy and affordable to achieve. Not easy to achieve, but much, much more affordable than other, $1 million systems that a lot of the industry is used to seeing and used to purchasing. When it comes to part costs, again, very, very dependent on the part itself. But I, just wanted to show an example of this. Parts that are good for Mantle's process are parts that are relatively complex. If it's something that's easy to machine today, it's probably going to be faster and cheaper to keep machining that. And we're certainly not ignorant to that. We understand there's certain applications that make sense. There's certain applications that don't make sense. The parts that do make a lot of sense generally are parts that require a lot of hard milling or a lot of sinker EDM time. For example, the part you're seeing on the left would have required a lot of sinker EDM time to produce all of those thin ribs. So just to show you an example of this part's going to take about 68 hours to print. So it'll take you about 2.5 days. It's going to go in the furnace for about a day and a half. It's going to cost you about $1,300 all in, including depreciation, labor, all consumables, et cetera, and cost about $400 in material. We tend to say we get you about 85% of the way there, which means this tool would just require a little bit of grinding to the outside, finishing of the gator and the ejector pins, and then you go ahead and shoot parts. To kind of continue on this same theme, just to kind of reiterate, what are the best parts that make the most sense with Mantle? Tools that require multiple machining setups or EDM operations to build traditionally. Like I just mentioned, parts that require lots of sinker time or parts that require a lot of hard milling. Tools that are needed for kind of challenging resins, things like peaks and acetals and radel that could not be molded with aluminum tools, even if it's just in the prototyping stage. The desire to use steel tools for actual product representative tooling, so you actually validate not just the part, but actually the manufacturing process as well. And then, of course, tools that can benefit from this conformal cooling process to incorporate complex cooling channels in there to reduce your cycle time. A couple of things, those are tools that are great for our process. A couple of ways to kind of optimize your technology and optimize your tools for our process is, of course, to use things like inserts. We get lots of people who, will ask me, they'll send me things on the left. They'll say, I want to print this, print it faster and less expensive than how you're doing it today. And I say, well, do you really want to print this or do you want to print what's on the right? For example, what's on the right would take a day to print, cost you about $500. What's on the left is going to take you 7 days to print. It costs you about $3,000. Chances are you can find a creative way to attach that insert to that big block a lot faster than we could print that whole big block by itself. So just finding ways to make sure you're printing feature detail rather than printing these big block materials. Another way is you get some economies of scale with our technology. So the ability to kind of print multiple parts at once. This is looking at a barb fitting example, but you can see printing one of these is going to take you about 36 hours. You can print 4 of them in about 75 hours. It also, of course, reduced the cost quite a bit because now we're not just depreciating one part. The depreciation time reduces from 1 to 4 parts across that time. So the ability to kind of print multiple parts at once is always a good idea when working with our technology. That's really all I had today. I'm more than happy to take some questions at this time. Thank you for joining me. I know this was a relatively quick webinar that we kind of, that was the goal of this, just to really quickly review some of these 9 different ways that our technology is designed for the shop floor. I'm more than happy to stick around and answer any questions, any comments. But thanks again for taking 20 or so minutes out of your day today to join me and talk about our technology and how it's really disrupting the precision tooling world. Thanks.